Hey friends, it's good to be back with you. In this lesson, it's time to learn about more efficient ways for solving ordinary differential equations. And before we can get too much farther, we have to decide what we mean by efficiency. Well, efficiency is, in this case, finding the right answer with as few calculations as possible. We've gone over up till now a couple of different methods for solving ordinary differential equations. We could try direct integration, which doesn't generally work. We've used finite differences. We've used Laplace transforms. And I've also used numerical methods in MATLAB and MathCAD without saying much about what they were actually doing. It's time to start saying more about that now. So when we talk about efficiency, we're talking about efficiency in numerical methods. And when you look at this, you think, why do I care how many calculations it takes to solve this? This is so simple that the calculations on any computer are essentially instantaneous. What do I care if I take a few more steps or require a few more points in a curve to approximate it? Well, these are homework-sized problems. In more practical applications, like engineering applications, sometimes evaluating y is really difficult. It's not just a simple equation like this. The guts of the calculation may take a long time. It may take a very long time. So it really matters in a lot of cases how efficient your algorithm is. Sometimes you can't afford too many calculations. Now, the example that everybody talks about is weather models. Weather models are extremely large. And when you see supercomputers and they're grinding away doing something, what a lot of them are doing is grinding out weather models. Well, the more points you can put around space, the Earth, the atmosphere of the Earth, and the more points you can take in time, the better your answer is going to be. But you have a time limit. If you're going to make a 24-hour weather prediction, you better be able to calculate it in less than 24 hours. It doesn't help much to go to some citizen and say, hey, my computer says you just got blasted by a hurricane about 2 days ago. We can't do that. So the model has to run fast enough to be useful. And because of that, the methods that are used to solve that model have to be very efficient. So we care about the efficiency of numerical methods for solving differential equations. Now with that, let's turn to a really simple problem. This looks like about as simple as differential equations get, isn't it? Let's start with a finite difference method. Now I'm going to start with the finite difference method you've seen before, which is a forward difference. And then we're going to find out there's a problem with it, but that problem can be fixed by going to a slightly different method. So let's start by just solving this using a finite difference method. Let's go ahead and say that y of n plus 1 minus y of n over dt equals minus 2.3 y of n. All right, we've seen this before. This is called a forward difference, and that's also called an explicit method. Let me write this out here for you. And it's called an explicit method. All right, I'll write that out here. There we go. So those are the two names you normally see associated with this. Well, this isn't very hard to solve in this form. All we got to do is solve for y of n plus 1 on one side of the equal sign and everything else on the other side of the equal sign. So let's do that. All right, all I did was multiply through by delta t right there, and then add that y sub n. Let me take one more step in cleaning this up. Let's put it over here. All right, it looks to me like I can say 1 minus 2.3 delta t times y sub n. All right, man, that's so simple a professor can do it. So you know what that's got to be like. If I know what one point is, I can calculate the next one. Well, I do. I've got this initial condition here. So if I say n equals 0, well, y of 0 equals 1. All right, there you go. Plug that in. I know what delta t is, because remember, This is a finite difference, not an infinitesimal derivative. Since it's a finite difference, I know what delta t is. It's a number, I've assigned it, I know what it is. So I can, if I know y0, I can calculate y1. If I know y1, I can calculate y2. If I know y2, I can calculate y3, and so on. All right? Looks pretty straightforward. Let's go ahead and go on to MathCAD, just because it's easy to look at. Let's go onto my computer and see what happens when we try to solve this.
Okay, I've taken a few minutes and programmed two things into MathCAD Prime. The first is I used ODE solve, which is the canned differential equation solver in MathCAD, one of them actually, to find what's effectively the exact solution. It's not quite, but it's awfully dang close. The second thing I did was to do the explicit finite difference solution we saw on the board. I guess I don't need that. That was just a check. So let's start up here. X final is 5, so I'm going to evaluate the answer, or develop the answer from x equals 0 to x equals 5. I'm going to use 10 steps, and so that gives me a delta x of 0.5. Now I need to do a little bookkeeping over here. I need to make a list of i's from 0 to n, and x's from 0 to n. Now MathCAD is one of those languages that will let matrix addresses start at 0. So that's why there's a 0 there, and I can just use the I there. I don't have to offset anything by 1. In MATLAB, the first matrix address is 1. And as I've mentioned before, some computer languages allow the first matrix address to be 0, first vector address, I guess, to be 0, and some require it to be 1. This just happens to be one of the ones that lets the first vector address be 0. So I need a starting point. There's x0 equals 0 and y1 of 0 equals 1. Now I'm saying y1 because eventually there's going to be a y2 in here. But for right now, there's y1. And this is explicit, which means that if you know y of I, you can directly calculate y of I plus 1. It's just go around and around and around and go as far as you want. So it's quite simple. Well, what does this look like? I made the plot earlier and just hid it off screen so I can show it to you quickly. There it is. Let me just scroll up here a little bit so you can see it. Now the blue is the exact answer, or the effective exact answer. That's the one that came out of ODE solve, which is the numerical solver in MathCAD. And the, I guess that's magenta, is the explicit finite difference solution. Well, it doesn't look to me like 10 is enough points. Let's go to 20, see what happens. Yeah, that's looking better. Now, right here, it's got the slope correct right at the starting point, but as the slope changes, the finite difference solution is not keeping up with it. So let's just keep going. Let's go to 30 points. Okay, closer. Let's go to 50. Closer still. So you can see that the slope eventually catches up, and I get the right answer there fairly quickly. If I want to track that curve right there, I need a lot of points. There's 200. Okay, now I've got it pretty close. Let's go back to 10. Let's go the other direction now. What happens when I go from 10 to 9? Okay, so it's oscillating a little bit, trying to get settled in there. Let's go to 8. Oops, 8. There we go. Well, it's having a harder time turning that curve, turning that corner there. Let's go to 7. Uh-oh. Okay, the errors here are getting bigger. In fact, for this particular equation, they get larger without bound once I get past a certain point. Let's go to 6. Okay, now it doesn't look like it's converging at all. It's coming very, very slowly maybe. And when I go to 5, I'm past some sort of stability boundary. The errors are actually getting larger as I go on in space and not smaller. So the solution is diverging. This is a problem that sometimes happens with forward difference solutions. This particular equation right there is a member of a class of equations called a stiff differential equation. Again, not my favorite name, but we're stuck with it. There's no rigorous mathematical definition of what constitutes a stiff differential equation, but it's enough to say that it's one that's not numerically well conditioned, that if you're not careful in the way you solve it, your approximate solution will not only be incorrect, but the errors in it will grow without bound. This is one of those times. So how are we going to solve that? That seems like a real deal breaker, because I pulled this out of, I can't remember where. I think it's off a Wikipedia page or a textbook. I can't remember which. You may see it as you go poking around the internet. I happen to know that's a stiff differential equation. What if I've got a differential equation and I don't know whether it's well conditioned or not? When I just blindly throw a finite difference solution at it, I might get an okay answer, I might not. Is there another way to go at this so I have a little more assurance that my solution will converge to the right answer, that it will be stable over a larger range of possible solutions or estimates? And the answer is yes. There's something called an implicit solution. So let's take a break from MathCAD here, go back to my board, and let's figure out what an implicit solution is.
All right, now I've cleared my board and I've written down the equation again, and there's our explicit solution. This is the one we found a few minutes ago. Let's try something different now. I'm going to do one thing. I'm going to rewrite this finite difference solution, finite difference estimate, I guess, finite difference approximation, with one change. All I'm going to do is I'm going to make that, instead of y of n, it's now y of n plus 1. This is actually a bigger deal than it might seem. With the explicit solution, all we knew was the slope where we were, and we were going to step forward based on that slope. Right? With this one, we've got y of n plus 1, y of n plus 1 there. It's really looking backwards. If you look at the right-hand side of the equation, that says here's where I am. Before, when this was y of n, it says here's where I am, here's where I think I'm going. When I put the plus 1 in there, it's here's where I am, there's where I was. That's a big difference. This one little change greatly affects the stability of the solution. This is called a backwards difference or an implicit solution. So backwards difference or an implicit solution. So all I've done, really, the only thing I've really done is I've changed that index from n to n plus 1. Well, how does that affect how we solve it? Well, it makes a difference. So let's try this. I'll do exactly what I did before. Okay, that's exactly what I did before, but now all the y of n plus 1s, they're in the wrong, this one's in the wrong place. It's on the right-hand side of the equation, not the left-hand side. Can I write down? Well, I can go down one more step here. So I can say this. All right. Now I'm gonna go up here. So I need some more room on my board. So let me take from here up to here. And what I'm going to write out is y of n plus 1 now equals there. Those are different solutions, aren't they? This is the implicit. That's the implicit solution. It looks different. And you can see the same constants in there, but it's a different form. Well, what is this going to look like? Let's go back to that MathCAD file we were working on a little bit ago, and let's plug this in addition to the curves that are already on that plot, and let's see what happens. Oh, one thing I wanted to note, on the MathCAD file, I just realized I was using y and x and not y and t. Sorry about that. Math doesn't care what you name your variables, so I apologize if you're getting a little confused going from one to the other. But in the MathCAD file, I was using x instead of t. It works the same way. So with that, let's go back to the computer and see what happens when we do the solution this way.
All right, now I've added the implicit finite difference solution alongside the explicit one. I've also zoomed in a little bit and reformatted a bit. By the way, those green boxes that go around some of the variables, that's MathCAD lingo for you're redefining something you've already defined. So right here with the X, it's just telling me I've already defined something here. Actually, I don't even need that. And right there with the Y1 and the Y2, I've already assigned the initial value, and it's telling me that I'm now redefining part of a vector. Well, I know that. That's part of the point. There's a way to turn those off, but it doesn't really matter for what we're doing. So what I've left everything else the same. I've set n equal to 20 as before, and I've added another trace. I'm calling it Y2 for the implicit solution. So let's see what it looks like on the plot. I couldn't fit it all on one page here, so we'll have to scroll up and down a bit. So there we go. Now the magenta is explicit. So the magenta with the rectangular boxes here is explicit. That's the forward difference. We've seen that before. And the new implicit solution is in red, and it's got dots on it here. Hopefully your screen's big enough you can see that. And you can see that the error is maybe a little smaller. As the number of points goes up, the implicit solution isn't appreciably better. I mean, it's not, the error is maybe a little smaller, but it's not remarkably smaller. There, one overshoots and one undershoots as we go around that corner there, around that curve. So as the number of points gets large, there doesn't really seem to be much difference. Let's go the other direction. Now let's start decreasing the number of points. Uh-oh. See where we had this before? The explicit solution way overshot and then kind of eventually caught up. The implicit solution isn't doing that. There's no hint of instability. This is starting to smell like instability on the way, and that's exactly what it is. So let's bump down. Let's go to maybe 8 points. Have it recalculate. There it is. Okay, the implicit solution, the error is growing a little bit, but the error is growing proportionally. Okay? It doesn't look like it's going to start growing without bound, and it won't. So let's sneak up on that stability boundary we found before, n equals 7. And as before, you can see that the error of the explicit solution is starting to grow. The implicit solution, it's a little more error, but not much. And again, no hint of instability. So 6. This is right on one side of that boundary. Okay, again, the explicit solution, the error is growing a bit, but there's none of this oscillation. There's no hint that the solution is going to grow without bound. And let's go past that stability boundary we found before. So now you can see that as before, the explicit solution has diverged. The error is going to grow without bound, but the implicit solution, it hasn't. Now there's some error here as it's going around that curve, but it eventually catches up with the curve. So the implicit solution will give you a stable answer and less error as the number of points goes on the curve goes down. So in the implicit solution is stable. Now is it absolutely stable? Well, it depends on the equation and some other things. But for this stiff differential equation, this equation that's poorly conditioned, the implicit solution doesn't have a lot of problem with it. The explicit solution diverges when the step size gets too big. So when we're talking about efficiency and what's the minimum number of points you can use and minimum number of calculations you can use to get an acceptable answer, the implicit solution has the advantage of being stable, where the explicit solution is not as the number of points goes down. Now I want to be careful that we don't draw too general a conclusion from this. I selected this equation specifically because it was poorly conditioned. Not all equations are. However, when you set out to solve a differential equation, you're not always going to know which one you have. In fact, many times you don't. Now, how often are you going to do this by hand? Well, I don't know. I don't know what's in your future any more than you do. But if you look at CAN software, analysis software, specifically structural and aerodynamic analysis software, if you go into the setup window, there's often a choice you can make. It'll ask you whether you want an explicit or an implicit solution. Well, you get to choose one or the other. The implicit solution is more likely to be stable and might require fewer points, but there is some computational overhead that comes with that. Now, rather than try to describe it in words, let me go back to the board. I'm going to make one change to the differential equation to show that the implicit solution comes with its own problems.
Okay, there's only two more things you need to know before we can be done with all this and move on. The first one is, why don't we just use implicit methods all the time? And the second one is, what's a Runge-Kutta method? You'll see it a lot, you'll use it a lot, and without getting into too much detail, probably a little bit of an explanation would be good. So, first, why don't we use implicit methods all the time? I mean, here's our two solutions we had. One of them isn't any harder to calculate than the other. They look different, but you know, the computer doesn't care. There's no more computational overhead with this one than there is with that one. Just use them all the time. Here's why. For this particular equation, it wasn't a problem. Let me make one change, just one. Okay, instead of that y of t, let's make it square root of y of t. Different equation, but you'll get the point here. So let's do this. Let's go ahead and say y of n plus 1. So that, just as before. Again, exactly what we had before. There, for the implicit solution. Okay, this is now a backwards difference, and we're going to go for an implicit solution. So let's do this. Okay. Okay, again, just followed the same process we followed before. I'm getting tired of writing down there. I'm going to write up here because I get to stand up straight if I do that. So let's do this. All right. Now, all I did before was I factored out y of n plus 1 divided by 1 plus 2.3 delta t, and we are good to go. Only I can't do that now. Well, now what am I going to do? Well, I guess I could square both sides? Nah, that's not going to help. Now what do I do? Well, here's what you're going to do. That's what you're going to do. Oops. And now what you have to do is you have to find a root. Okay, this there's no closed form way to do that. Nothing comes to mind immediately here, at least. Now you're going to have to go to a root finding algorithm to figure out what y of n plus 1 is. With the explicit solution, you don't have to do that. If you know what y of n is, you just execute some calculations and y of n plus 1 just comes out. You don't really have to pay much for it. With this one, now what are you going to do? In order to find out y of n plus 1, now you have to find a root, and root finding is expensive. It's more expensive than the explicit. So nothing comes for free here. You can use the explicit solution. It's faster, it's easier, but it isn't necessarily stable. The explicit solution is stable, but it's generally more expensive to execute because there's usually a root finding step in there. So that's the problem. So that's why you would have to think a little bit before you chose explicit or implicit. Now, the example I used before was pretty careful to choose one that was A, poorly conditioned, and B, easy to evaluate. So it was a good learning exercise, I hope. But you don't have to do much before all of a sudden implicit comes with some overhead. Now, that was the first thing we need to know. The second thing we need to know is Runge-Kutta. And let's use an explicit solution here. Okay, I rewrote this. Let me make that y of n. Now, I was pretty careful to put the y of t at the back this time. That is this, right? That's a slope. That's what that means. What's on the right-hand side of an equation is a slope. So you multiply your slope by delta t, add where you were, and off you go. Y equals mx plus b. This looks an awful lot like a straight line. Now this is the slope where you are right now. This is the slope at t of n, wherever that is. Now, it's an estimate. Could you improve that estimate? Sure. What if you did something to that to correct for the fact that the slope is okay where you are, but as you step forward, the slope's going to change? Could you put a correction term in there? The answer is yes, and that's what Runge-Kutta does. There are different orders of Runge-Kutta. Second, third, fourth, and fourth, fifth is usually what you see. And if you look in MATLAB, there is ODE 2.3 and ODE 4.5. Well, ODE 2.3 is a second, third order Runge-Kutta, and 4.5 is a fourth, fifth order Runge-Kutta. And the difference between them is how sophisticated are they in updating that or refining that estimate of slope. It takes information from where you are plus information at a couple of other points. And in exchange for the additional calculations, what you get is a much better estimate of where your next point should be. In fact, it's good enough that the ODE 4.5, the fourth, fifth order Runge-Kutta, is pretty much the default for ordinary differential equations. As long as they're not stiff equations, this works pretty well. Now, there are a bunch of solvers out there for stiff equations, and they differ from Runge-Kutta. So if you're using MATLAB and you have an initial value problem, if you don't know what else to do, pick ODE 4.5. That's generally the right answer. As long as your equation is not really badly conditioned, that is, it's not a stiff differential equation or it has some other weird problem characteristic about it, the fourth, fifth order Runge-Kutta will probably work. There's a help file or help page in MATLAB that'll even help you pick which differential equation solver to use, and it's pretty informative, so check it out. So I think we're done with the topic here. It's time to move on. Hope this helps, and we'll talk to you next time.